We talked about the rate constant, and as the name suggests, it's a constant, but as it turns out, it's only constant if the temperature remains constant. The rate constant does change with the temperatures. A lot of chemical reactions are very sensitive to temperature, and so if you increase the temperature, they typically go much faster. A 10 degrees Celsius increase in temperature could double or even triple the rate of a typical biological reaction. And this is one of the reasons why your body regulates its temperature so closely, is because if we're getting too cold or too warm, now the reactions that keep us alive are not going to be in sync with each other. So the temperature dependence of the reaction rate is in the rate constant. Rate constants generally increase with temperature, and that's why the questions we were doing on Monday, it would say at 720 Kelvin or at a constant temperature, because it's only a constant at a constant temperature. So we have an equation that gives us the relationship between the rate constant and the temperature in Kelvin, and this is called the Arrhenius equation. And, again, this is one that's given on your information sheet for exams, but we need to know how to use it, right? So here, the rate constant is equal to a frequency factor times an exponential factor. And so this is E raised to the power of negative EA over RT. EA is an activation energy. R is the gas constant. For units, we need to use the value 8.314 joules per mole Kelvin, not the liter atmospheres one. And the temperature, again, has to be in Kelvin, okay? So what does this thing mean? What's activation energy? What's the frequency factor? Even if a reaction is energetically favorable, often it needs a little boost to get started. So here we have an example of hydrogen and oxygen reacting to form water. So we've got, this is an energy diagram, we've got the energy of the reactants, they have a certain amount of energy. The energy of the products is much lower. And where does that energy go? It goes out into the surroundings. So most people understand that if you mix hydrogen and oxygen gas, you can have a pretty sizable explosion, right? Highly exothermic. And yet you can also have hydrogen and oxygen gas just like hanging out in a balloon together, not doing anything. Why don't they react immediately? Because there's this activation energy. There's a barrier they have to get over. If you take a candle and touch it to the balloon, if you spark a mixture of oxygen and hydrogen, it will explode. That spark is what gets it over the hump here. Once you get a couple of these going over the hump, then as this reaction occurs, it produces plenty of energy to get the others over the hump. So that's the activation energy, an energy barrier that needs to be overcome before the reaction can occur. And then the frequency factor. So we can think of this as the number of times that the reactants approach that barrier per unit time. So I don't know why, but this reminds me a little bit of playing miniature golf, putt-putt golf. And so let's draw some bad pictures because that's always entertaining. So here you have your person, and they've got their golf club, and they're trying to hit this ball over the hump so it can go down there and hopefully at least get close to the hole, right? So you hit the ball, and does it always go over the first time? Well, it depends on how hard you hit it, right? Sometimes you have to take several swings at it because the first time you didn't give it enough to get over the hill. And so that's a little bit what the frequency factor is, well, how many times did you swing at it before you got it right and it went over the hill? So let's think about a reaction in which methyl isonitrile rearranges to form acetonitrile. So here what we have is some bonds breaking and then reforming. So the nitrogen and the carbon are switching places. In order for that to occur, though, this single bond has to break, and this has to turn around. And then it remakes a single bond with the carbon. The triple bond can stay there. Okay? So how can this occur? Well, the molecule goes through an intermediate state, which is at higher energy. And that's where that carbon-nitrogen triple bond goes sideways. And that weakens the bond with nitrogen, and then you can go back this way or you can go forward. So you're like teetering here on the fence. And if you go forward, it releases a lot of energy. If you go backward, it releases some energy. So energy is needed to twist this guy, to make it more ready to react. It needs to have higher energy to react. That's the activation energy. So the activation energy is the amount of energy needed to reach that activated complex or transition state. So we need a certain amount of energy to twist this, and once that's twisted, it can react. Any questions about that? If you have a higher activation energy, you're going to have a slower rate because more energy is required at that given temperature to reach this hump. So what's the frequency factor? Well, we said it represents the number of approaches to the activation barrier per unit time. So that NC group approaches the activation barrier each time it begins to rotate. So this begins to rotate, that bond weakens. That's approaching this state. Is it going to go all the way to become that state? We don't know. So they talk about this NC group wagging, like a dog's tail is wagging. And so, the dog's tail is, the dog's a little bit happy, or you just came home after a long day and the dog's tail is going all over the place, right? The frequency factor is the rate at which that group is wagging, vibrating side to side. Each time it wags, you're approaching this activation barrier. So that's the frequency factor. This is all kind of weird stuff. Does anybody have any questions? You're either all okay or I lost everybody. Or maybe you're not awake yet. It's okay. So that was the frequency factor A. The exponential factor represents the fraction of molecules that have enough energy to go over the activation barrier on any given approach. So that exponential factor is going to be a number between 0 and 1, and that represents the fraction of approaches that are successful. So we have approaches to the hump, and we have approaches that are successfully going over the hump. So, playing miniature golf, maybe, it's been a while, and you're putting away, and you keep just not getting it over the hill, right? You're approaching it many times, but maybe only 1 in 5 times you get it right and it goes over the hill. So here's an example. If the frequency factor is 10 to the 9 per second, so 10 to the 9 approaches every second, that's a lot. And the exponential factor is 10 to the minus 7. That means 1 out of 10 to the 7 of those approaches is successful. So the frequency factor, that's the A, and this is the e to the negative EA over RT part. So then the rate constant is equal to the frequency factor times the exponential factor. Multiplying these, we get 10 to the 2 per second. We're not going to do many calculations like this. I just want you to understand what these numbers mean. Any questions? So let's talk about that exponential factor a little bit more. So the exponential factor depends on the activation energy, and it depends on the temperature. So if this exponential factor is larger, closer to 1, then we have more approaches being successful. So if we get to 1, that means every approach is successful. You get the ball over the hump every single time. If that factor is 0, that means you never get it over. None of your approaches, none of your putts are successful in getting it over that hump. So when the activation energy is low and the temperature is high, then this exponential factor is going to be getting closer to 1. And the reaction is more likely to occur because we have higher energy. We need a lower energy to get over, and we have a high temperature. So e to the negative this, blanking, sorry. So if this is low and that's high, then this is a very small number, right? So in order for that factor to be equal to 1, we need e to the 0, right? So as this part gets smaller and smaller with low activation energy, higher temperature, this whole factor can get closer to 1. If the energy, activation energy is high and the temperature is low, this number gets bigger, and the overall factor approaches 0. Okay, so then no approach is successful. Questions? Let's look at the effect of temperature. We learned in Chem 1A that temperature is a measure of the average kinetic energy of a substance, the particles in a substance. And we learned that molecules in a given sample have a range of energies. The temperature is the average, but some are slow and some are high. And so that will typically follow some sort of a distribution where most of them are in here, but some of them are high and some of them are really low. When we increase the temperature of a substance, this distribution moves to higher energy, but it also spreads out. So it's getting broader, and so now the number of particles that have enough energy is larger and significantly larger. So we increase the temperature, and now we have a lot more particles that have enough energy, that meet the activation energy. So this is a summary. The frequency factors, the number of times that the reactants approach the activation barrier per minute. The exponential factor, the e to the EA over T negative, is the fraction of approaches that are successful, that actually go on to a reaction. And that exponential factor increases with increasing temperature, but decreases with increasing activation energy. So this part here, if you just think about it, makes sense. So if this is a big barrier, is that going to help my reaction go faster? No. So if the activation energy is higher, then the rate's going to be slower. If my temperature is higher, that means that more of these have more energy, and they're already closer to the activation energy, and so that's going to make the rate go faster. So that exponential factor increases with increasing temperature. Now more approaches are successful, but if you increase the activation energy, fewer are successful. Okay, let's see if we understand. So which of these statements best explains why reaction rates generally increase with increasing temperature? Choice A. Reaction rates increase with increasing temperature because as temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. What do you think about that? Sounds good, right? Sometimes it's scary when the first one sounds right. Let's look at B. Reaction rates increase with increasing temperature because as temperature increases, the pre-exponential factor of the rate constant increases. What do you think about that? True or false? False. That pre-exponential factor, the A, is not dependent on temperature. So B is not a correct choice. C, reaction rates increase with increasing temperature because as temperature increases, molecules decompose into their constituent atoms, which can then form new bonds to form the products. Hopefully that sounds a little ridiculous, right? It's just like really not at all what we've been talking about. That's one of those things that if you know nothing about what we just learned about, that might sound reasonable. So the choice is A. Any questions? So here's our Arrhenius equation. You got the frequency factor, activation energy. How can we know what these factors are? Well, we can find them by measuring the rate constant at different temperatures. So we have to do an experiment. So we'll keep the concentrations the same, and we'll change the temperature and measure the rate. And we can rearrange this equation into a linear form. So if we're taking the natural log of both sides, and we end up with this. That's a linear form. So y equals mx plus b, right? So b is the natural log of the the frequency factor. Y is the natural log of the rate constant. EA over R is the slope, negative EA over R. And 1 over T is X. So we graph the natural log, so we measuring rate constant, we take the natural log of the rate constant versus temperature, so we have the temperature measured in kelvins, and we find the reciprocal, 1 over the temperature. And then we graph this on the y-axis, this on the x-axis. And we should get a straight line, or close to a straight line. So we have Excel, or whatever program you use, find the best straight line fit to that, and it'll give us an equation. And from that equation that the computer gives us, we can find EA from the slope, and we can find A from the intercept. Well, A, that the frequency factor actually is a little bit dependent on temperature. But it's pretty small, and so we're going to ignore it because we can for our purposes, okay? But just telling you the truth, there's a little bit of temperature dependence, but it's small enough that we can ignore it. Okay, so here we're looking at the decomposition of ozone, which is very important in a lot of atmospheric reactions. Ozone decomposes into oxygen and an oxygen atom. And they studied the kinetics of this reaction, and these are the results they got. So looking at it at different temperatures and measuring the rate constant. What do you think the order of this reaction is? Based on the units of the rate constant is the only way we could tell. Second, yeah. So we've got these numbers in our spreadsheet, and we calculate 1 over the temperature. We calculate the natural log of the rate constants. We put it in a graph, and it looks like this. So find the value of the frequency factor and the activation energy for the reaction. So here we have the equation for the line, and that corresponds to the linear form of the Arrhenius equation. Nice if I use the same colors, but I'll probably mix them up. So the natural log of A is equal to the intercept. Negative EA over R is equal to the slope. Natural log of K is Y. That's what's on the y-axis. 1 over T is X. That's what's on the x-axis. Maybe let's color those in too. Do you see how those two equations line up with each other? Bless you. Our graph, natural log of K on the y-axis. So this is what Y is. Y is this guy over here. Why? Because it works out that way. On the x-axis, we have 1 over temperature. So here, we wrote this in a way that 1 over temperature is kind of standing by itself so we can see it clearly. So that's X. The slope of that line is equal to negative EA over R. The intercept is equal to the natural log of A. So how do we find the frequency factor? Well, the frequency factor is A, and the natural log of A is equal to 26.8, because that's what the linear equation tells us. Okay? So to solve for A, we do e to the x on both sides. And this is 4.36 times 10 to the 11th. And the units of the approach factor or the frequency factor are seconds to the minus 1. Any questions? How do we find the activation energy? Well, negative EA, the activation energy, divided by R is equal to negative 1.12 times 10 to the 4. When we look at this intercept and we try to say, well, what are the units on that? It's kind of meaningless, right? Because it's the natural log of something. So we're not going to worry about that. If we look at the slope, so we essentially treat this, because it's a natural log, we say that it doesn't really have units. And so then what are the units on the slope? Well, the slope is the rise over the run, right? The change in y divided by the change in x. Well, the change in y has no units. And the change in x, that's 1 over Kelvin. So the slope has units of Kelvin. The units here are not a big deal, but I just want to show you that they do work out. So this would be 1 over Kelvin. Well, how do we solve that? Well, we can isolate EA, multiply both sides by negative 1, and then multiply by R. R is 8.314 joules per mole Kelvin, and that's multiplied by that slope, 1.12 times 10 to the 4th, 1 over Kelvin. The kelvins are going to cancel out. 8.314 times 1.12 times 10 to the 4th. Again, you should have your calculators out. 93116.8. What are the units on this? They come from the units here that are left, joules per mole. When we look at the answer is given in kilojoules per mole. This is kind of a big number, and instead of writing it in scientific notation, we can just use a larger unit. So kilojoules is 1,000 joules. So that's the same as 9.31. And again, as often in this class, we'll figure, 3 sig figs is probably good. 9.31, no, 93.1. 93.1 kilojoules per mole. We're moving this over 3 places. 1, 2, 3. If you don't want to mess around with units in here, that's absolutely fine. But then you do need to know what the units are of the ultimate answer, right? So the regular units that are used in all of these calculations are joules, not kilojoules. And that will be tricky sometimes, and it will be tricky on exams. So it's joule here, joule per mole, and the temperature always has to be in Kelvin. Whoa, the time is always in seconds. I bumped my iPad, almost dropped it on the floor. Any questions? Let's see if the answers are right. Yes. Okay, So for the decomposition of ozone in that example, use the results that we just found to predict the rate constant at room temperature, 298 Kelvin. Well, because I have a bad memory, I typed them in there so we don't have to worry about it. Okay, so that's what we just found. So we'll use the Arrhenius equation. The rate constant is equal to the frequency factor. I always want to say activation energy because it starts with an A, right? Capital F would make more sense, but we use that for something else, so it's A. Approaches, maybe. The frequency factor times e to the negative EA, there's our activation energy, over RT. So we're wanting to find K, so we can plug these things in here. So 4.36 times 10 to the 11 e to the negative, this is in kilojoules. It needs to be in joules to do this calculation. It's going to be seriously messed up if we don't. So this is the kind of thing that I will try to trick you with on an exam. So watch out for that. When we're doing the calculation, we need joules here because the gas constant has joules, right? So how do we make kilojoules into joules very quickly? Change the K to what it means, times 10 to the 3. So instead of writing K, I'm going to write times 10 to the 3 joules. If you were in my 1A class, we did that a lot. If you weren't, this might be something new. This is not proper scientific notation, but your calculator doesn't care. So you can just type it in like that, and it saves the problem of, do I move it to the right, to the left? We should have K, kilo means 1,000. So instead of writing kilo, we write times 1,000. So that's EA, and then this needs to be divided by, okay, I did not plan my space wisely. So because I can, I'm going to move it. Divided by R, 8.314 joules per mole Kelvin, times the temperature, 298 Kelvin. And then you got to plug this into your calculator. Here we're dividing by two numbers that are multiplied. So what most students find best is to use parentheses there because you naturally want to multiply. So get your calculator out and make sure it's going to cooperate with you. So I'm doing 4.36. Did that wrong already. 36. EE for times 10 to the 11 times E raised to the power -1 93.1 EE3 divided by, open parentheses, 8.314 times 298, close the parentheses. 2.0891 times 10 to the minus 5. Did you get that number? 2.075. Okay, let me check. Oh, 36. 8.314. 298.
Instead of the 90, we put 1 times 23rd. I just put the full number in instead.
It should be the same. What did everybody else get? You get my answer or her answer? You got 0. Okay. So that calculator has a problem. What did the rest of you get? Did you get this one?
I got hers.
You got hers. Okay, interesting. Interesting.
The answer says
Okay, we solved this problem. This is the rounded value. We actually had a lot more digits in the earlier example. And so when you type all those numbers in, instead of the rounded value, you get a slightly different answer. So, which is better? Rounded numbers or unrounded? Unrounded numbers are always better. So your answer's better than mine. Do you need me to look at your calculator? You, Ting? Do you need me to look at it, talk to it? Yes, okay. Okay, so, we would probably report this with 3 sig figs, so I'm getting 2.09 times 10 to the minus 5. What are the units on this rate constant? Are we going to get them from the units over here? No. It's going to be whatever the units are for this reaction based on its order. Do we know what those are? Yeah, it's m to the minus 1, s to the minus 1. How do we know that? Because they told us over here. That is not something I'll try to trick you on. But if there's a problem like this and they put these units on the rate constant at the end and you're like, where did those come from? Units get kind of weird when you're using exponents, logarithms really. Okay, so that's what we got. Oops. There we go. And here, the answer the book gives is 2.07, which was Cash's answer, and a couple other people's answer. And that answer is better than mine. Does it make mine wrong? No. Because assuming that this is correct or correct-ish sig figs, this is an uncertain digit. I got 9, they got 7. Is that a deal breaker? Absolutely not. We expect some disagreement there. Any questions about that? I think that's something that's hard for a lot of students to accept because you've always thought of numbers as like precise things. Like 1 plus 1 is 2. There's no uncertainty. But when we have measurements and we're adding them together, then we do have uncertainty. It's unfortunate, but it's just the way the world works. Okay, what if we don't have a lot of data or we just really don't want to graph the stupid thing? What can we do? This is called the two-point form of the Arrhenius equation. And this is derived from the linear form. If you're interested in how that works, we can talk about it later. Most of you are like, no, I believe you. We'll just use that. That's in your sheet of equations also. So if we have temperature and rate constant for one, and rate constant or temperature for the other, we can calculate the missing one. There's 4 variables here. We have 2 temperatures, 2 rate constants. So we plug in the information that we have and we solve for the thing that's missing. Let's do that. Reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is 2.57 per molarity per second. And at 895 Kelvin, it's 567. Notice it's much higher at this higher temperature. So here what we have is two sets of data, and we want to find the activation energy. So I kind of got ahead of myself. Over here, if you know what the activation energy is, you can find one of these other variables. If you know these other variables, you can find the activation energy. So here we're doing that. So I'm going to identify what these things are. I'm going to call the first temperature, temperature 1. That's a kind of ugly 701 Kelvin. And then the first rate constant is 2.57, molarity of the minus 1, S to the minus 1. Temperature 2 is 895 Kelvin. It's pretty toasty. And K2 is 567. M to the minus 1, S to the minus 1. You want to identify which ones go together so you don't get them mixed up. Okay, then we have our equation. Almost messed that up. When you're working out problems, even if you can do a lot of the stuff in your head, there's certain steps that you really, really, really should write down. You should write down the equation that you're using. And then plugging the numbers in, you should write it with all the numbers plugged in. So the natural log, and I'm going to plug these values in, K2, 567, K1, 2.57, is equal to negative EA, that's what we're trying to find, over R, 8.314 joules per mole Kelvin, times 1 over T2, 895, minus 1 over T1, 701 Kelvin. Why do we want to write this out? So that we can see if we put the numbers in the right place. If we do the calculation and we come up with the wrong answer, if we have no work shown, we're just going to have to start over again, and we may just make the same mistake. If we have some work written down, we can see, well, am I using the correct equation? Did I mess something up in the equation? Did I mess something up when I was putting these things in here, right? Now we solve for EA. So again, I think it would be really nice to do this with the solver on your calculator, right? So again, if you want to use one of these and do the solver, just say, hey, pass me one. So I'm going to do natural log of 567 divided by 2.57, close the parentheses. And I'm going to go over to the other side and negative, and then I'm just going to use x as my variable, and that's going to be divided by 8.314. And then I'm multiplying by the quantity, 1 divided by 895 minus 1 divided by 701, close parentheses. Press equal. It shows me a meaningless value of x. I'm going to say, make that 0, and I'm going to press enter 2 times. And I'm getting this number. EA 145.096.7801. Anybody else get that? Now I'm just, for my own purposes, I'm going to do this without using the solver. Oh, I get the same number. Yay. Yay me. Anybody having trouble getting the correct answer? I plugged it in wrong. Lots of calculators have this feature, but this calculator has the feature where you can scroll up and see the actual numbers that you punched in. So you can see, oh, I pressed the 2 button, but the 2 didn't get in there. And that's why it's wrong. So that's a really useful feature as well. We're using our calculators in more sophisticated ways than we did in Chem 1A. Right? The math has gotten a little bit hairier. But if you have the number solver, you don't need to worry about it, right? I mean, you really don't need to know much math. You're given this equation and these values. You identify them, you plug them in the correct places. You type this equation into the number solver just like it looks, and it finds it for you. Amazing. Okay, so what are the units on EA here? Well, it's an activation entity. This would be joules or something, right? The units on our rate constants just canceled each other out. And there's a natural log over there, so that doesn't help much anyway. Here, the kelvins are going to cancel each other out. And so even if you don't want to think about how the units are going to cancel, joules per mole is in there, and so joules per mole is the unit here. But that's not what they asked us for. They wanted kilojoules per mole, right? So kilojoules we need to divide by 1,000. So we're going to end up with 145. And let's just stick with that, kilojoules per mole. Any questions? So they've got 1.5 times 10 to the 2. So in scientific notation, this would be 1.45 times 10 to the 2. And maybe they know something we don't. If we round this to 2 sig figs, 1.5 times 10 to the 2 is the same. Your exams are going to be multiple choice, but then there will be selected problems where you need to show some work. So if this was an exam problem, one of the choices would be this number or a slightly rounded version of that number. Another choice would be one of these, not both of them, because I'm not trying to trick you with sig figs here. I am trying to trick you with some units maybe, some other things, but I wouldn't give you both of these and make you pick this one. Because there's no way, just looking at this, that you'd come up with 2 sig figs. And I mean, me looking at it, I don't know how they came up with 2 sig figs. I'm just going to believe them because I don't want to deal with it. Okay? But I'll ask you to show your work. And so I want to see something like this. Like this would be the bare minimum for showing your work. The equation with the units plugged in. If you just pick an answer and it's correct and no work, you're not going to get credit on that particular question. So you kind of have the benefit of multiple choice where if your answer is not one of the choices, you know you screwed up, right? Getting one of the answers is a much better sign, except that I also know what kind of mistakes you're going to make. Oh, they're going to forget to convert to kilojoules, right? And so that'll be on there to catch you on that one. And then there'll be some other ones that maybe just kind of random. Any questions? Okay, using the results from example 15A, example 15. So this is example 15, and this is for practice 15.8. So in the textbook, they have an example that's worked out in the book. It may or may not match exactly the way I'm doing it. And then they have another one for practice where you can look up the answer in the back of the book, but they don't show you how to do it. And usually those are the ones that I do in lecture, but this one builds on another one, and so we're doing both of them. Use the results from that example and the given rate constant of the reaction at either of the 2 temperatures to predict the rate constant at 525. I did not think to pull numbers in here. So we need the activation energy. So I'm going to copy that. Whoops. Forgot how to paste things. Okay, so that's the activation energy. We need that. We also need one of these pairs. 701 with 2.57 or 895 with 567. I'm going to use the 895 with 567, 895 with 567. 895 with 567, 895 with 567. Ooh, got it. Okay. So temperature, we'll call that temperature 1. And this is rate constant 1. We're predicting the rate constant at 525. So temperature 2 is 525 Kelvin, and rate constant 2 is what we're trying to find. Any questions? There's a little bit of effort involved in figuring out, well, what do I need so I can solve this, right? We're going to use the 2-point form of the Arrhenius equation. So I'll write that down. Natural log K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. So we're going to plug all these values in. Natural log K2 is what we're trying to find, divided by K1, which is 567. That happened to be molarity to the minus 1 seconds to the minus 1, that's Kelvin. Natural log of that whole thing is equal to negative activation energy. Because we've got the gas constant here, 8.314 joules per mole Kelvin down there, we need the activation energy in joules per mole. So that's why I copied this one, and it's always best to use the unrounded one. And if you don't want to put all of those digits in, because there's an awful lot of them, use at least 2 extras. If you have 2 extras, it's not going to matter. If you want to write them all, great, do it. 14509. I'm just going to round it to the nearest 1 because that seems easier for me. Joules per mole. So that's the activation energy. I took this number. We originally thought maybe 3 sig figs, so that'd be 2 extras, and then this one, it was just easier to not mess with rounding up so much. Or if you had 2, they gave it to us with 2 sig figs, so having at least 2 over here, you get the idea. Temperature 2, 525 K, minus temperature 1, 895 K. Solve for that guy. And I think the solver is the best way to do this. I know that a lot of you are not really on board with the solver. So if you like the solver, you do it with the solver, and I'm going to do it without the solver, and hopefully we get the same answer. I'm going to simplify all the numbers that I can. So I can calculate this beast over here. Then I need to do e to the x of both sides. That'll get me K2 over 567 is equal to e to the negative 13.743. And so I'm going to take this result, and I'm going to multiply by 567. Anybody get the same answer? You got no sign change error. Okay. So on the solver, you may sometimes get no sign change error. And that is because it is solving this by iteration. And so it's always a good idea to go back and check that you entered the thing correctly. And here the equation is just fine. So it looks like the last time you started with whatever was left in x. So when you did this before, you came up with this answer, right? And so that answer is still sitting there as x, and you didn't put it to 0. You don't always have to put it to 0. But if you get no sign change error, that means you have to give the calculator a different starting point. So I'm going to try doing it from 0 and seeing if we get a better result. Yes. Okay?
How did you get it to like go to 0? Oh, just like right from
Yeah, just right there.
Okay.
So that's one thing you have to watch out for with the solver. It's usually starting with x equals 0 is fine. But if it's approaching a function from one direction, it may have trouble. So if we have it approach from the other direction, it might be more successful. Any questions? The question was, does it matter if you're calling this T2 instead and you're searching for K1? Is that okay? Yeah, it's fine. If you're using the solver, it's going to make absolutely no difference. If you're doing it this way, if you're looking for K1, K1's in the denominator, and it's just a little harder to solve for. K2 on the top is easier. Yeah, great question though. Anybody else? So there will probably be a question like this on the exam. So you need to make sure that you have a good relationship with your calculator, right? So I got a slightly different answer. I got 6.10 basically, and they got, 6.13. Is that a problem? No. Chem 1B, that's not a problem.
I got the same thing. I got the same thing that you did.
Okay. She got the same thing. That makes me feel better. They might have used a rounded number here. Who knows? Multiple choice, though, right? I would not put both this answer and the answer I got and expect you to choose between them because they are both correct. You do need to have a good enough understanding of significant figures that if you get an answer like mine, if you get this answer and this one is the closest choice, you should recognize that you didn't like completely screw it up. Yours is just slightly different, and this is still the correct answer. Okay? So, reaction A and reaction B have identical frequency factors. But reaction B has a higher activation energy. Which reactant has a greater rate constant, a larger rate constant at room temperature? Did you say A? Yeah, it was just so quiet I couldn't hear it. It's A. Two ways you could solve this. You could think about the Arrhenius equation. K is equal to that mess. And you could say, okay, well, if B has a larger EA than A, how's that going to affect the rate constant? Or a larger rate constant means a faster rate. So if this is at as room temperature and we're looking for which one has a greater rate constant, that's the same as which one is going to be faster. The one with the big hump to get over or the one with the little hump to get over? The one with the little hump, right? So it's going to be A. Any questions? The collision model. So we've been talking about just a single reactant because it's simpler that way. What if we have two reactants? This is very common. So we're going to look at two reactants in the gas phase. And so a chemical reaction will occur if those two particles collide, they bump into each other, and there's enough energy there to get over the activation energy. So each approach to the activation barrier is a collision between the reactant molecules. The frequency factor, though, is usually less than the number of collisions per second, meaning not all of those collisions end in a reaction. Why is that? I kind of said it already. Sufficiently energetic. There's that activation energy, right? If these two molecules just like barely bump into each other, they don't have enough energy to get them over the hump. They're just going to bump and move on. If they have enough or more energy, if they're smashing together, then they'll react. Is they have to have enough energy. So here we have an illustration of that. These guys are bumping into each other, but they're not reacting. These guys, this is meant to show they're going fast, boom, right? And so these guys are going to react, but these that are just casually bumping into each other are not. So we're going to watch this video because I think it's cute.
Have you ever been to a demolition derby? Basically, a bunch of people driving cars around the field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course, is to damage the other cars so badly that they can't be driven anymore. The driver of the last operational car wins. You know Crash Course Chemistry well enough to know that I probably wouldn't have mentioned this if it didn't have some relation to chemistry, so yeah, it does. Chemical reactions basically work just like this. Atoms and molecules move around their environment, occasionally ramming into each other. If they do it just right, a reaction happens between them, and if enough of them do it, the concentration of the reacting molecules will go down, while the concentration of the products goes up. Win. But it's not as simple as it sounds. For demolition drivers or for chemicals, in both cases, a lot of the collisions that occur have very little effect on the end result. One molecule hitting another doesn't mean a reaction is going to take place, in the same way that just randomly bumping into another guy's car doesn't mean that you're going to ram him out of the derby. So, what makes a collision effective? The hit has to be hard enough, and it has to be aligned just right. The branch of chemistry that studies how these collisions affect the rate of reactions is kinetics. And if you ask me, it's just as exciting and a heck of a lot more useful than demolition derbies. If only they sold funnel cakes in chemistry class.
I highly recommend this channel, by the way, Crash Course Chemistry.
So, if chemical reactions only work when particles bang into each other good and hard, just how hard do they have to bang into each other? Every reaction has a minimum amount of energy required to get it started. This is known as the activation energy. Molecules require this much energy to hit other molecules hard enough to break them apart and reform them in different ways. Without it, nothing will happen. It's like a hill that molecules have to get over before they can go any further. So where do they get this energy? Well, it's kinetic energy, the actual speed of the particles. So just like the cars in Demolition Derby, all else being equal, the faster the particles move, the harder the collision will be. But still, no matter how hard they hit, it won't do any good if they're not hitting the right way, in the right places. Like if you keep smashing into the back of a guy's trunk, that's not going to stop his car. There's no engine back there. You can bang Velcro together all day and night, and if it's not turned the right way, it'll never stick together. Same thing with molecules. As an example, take nitric oxide, one of the byproducts of gasoline combustion, and something that you can smell quite clearly at a demolition derby. Under the right conditions, it reacts with hydrogen gas to produce nitrogen gas and water. But the molecules have to hit each other just the right way. To make N2, two NOs have to collide in such a way that the nitrogens are together, and to get H2O, a molecule of H2 has to collide with the oxygen side of an NO molecule. Just like Velcro being turned the wrong way, you can smack the N side against the H2 all day and you'll never get any water from it. Now let's say that we're having a lot of solid, effective collisions between the molecules. The reaction should hum along with no further hindrances, right? Well, yes and no. Once the energy requirements are met, the reaction will proceed, but its speed or reaction rate will vary wildly from super fast to super slow. So the reaction rate, that's the rate at which the concentrations of the reactants decrease, and this has to be determined experimentally. It can't be calculated from the energy change or any other thermodynamic factor. One useful way to think about the rate is a quantity called the reactions rate law. It describes the relationship between the initial concentrations of the reactants and the rate at which they react. The rate law for a reaction is written like this. The rate equals a constant K times the concentrations of each reactant raised to some power. Notice that only the reactants are used for this, not the products. The rate law for our nitric oxide reaction then ends up as K times the nitric oxide concentration raised to some power times the hydrogen concentration also raised to some power. So you're probably wondering about all those raised to some power, like what power, and you should be wondering that. The exponents in rate laws are tricky, even for professional chemists and engineers, because like I said, they can only be determined experimentally. It's kind of intense, but we can handle it. Check it out. Suppose we did the reaction a few different ways and calculated the rate for each instance. Let's say that with the first reaction, we got a rate of 0.0060 moles per liter per second. Then we repeat the reaction with the same amount of nitric oxide, but this time with twice as much hydrogen as before. And now we find that the rate of the reaction is 0.012 moles per liter per second. What does this tell us? Well, doubling the hydrogen doubled the rate, meaning that the rate and the H2 concentration change in exactly the same way. So in the rate law, this can be expressed by the concentration being raised to the power of 1. Finally, we do it one last time with the original amount of hydrogen, but twice as much NO. And this time we find that we get a rate of 0.048 moles per liter per second. Doubling the nitric oxide caused the rate to increase by 8 times, and that can be expressed in mathematical terms by cubing the concentration term. This means that the final rate law for this reaction is K times the concentration of hydrogen gas to the first power, you don't need to write out the 1 obviously, times the concentration of nitric oxide cubed. A rate law in this form is said to be of the 4th order. We get that value by adding the exponents together, 3 plus 1. There is some math that isn't hard here. That equals 4. 4th order reactions are actually quite rare. Most reactions are of the 0, 1st, or 2nd order, but in all cases it's calculated exactly as we have done here. Now if you've watched our episode on equilibrium, this formula should look familiar to you. Equilibrium expressions also use bracketed concentrations with exponents, and that's no accident. Those formulas come from these ones. A reaction is at equilibrium when its forward and reverse rates are equal, right? So if we were to find the reverse rate law for a reaction, it would take the same form as the forward one, but using the initial concentrations for the products rather than the reactants. Think of like an imaginary reaction A plus B yields C plus D. The lowercase letters represent the coefficients of the reactants and products. The forward rate law is K times the initial concentration of A raised to some power times the initial concentration of B raised to some power, and the reverse is the same, but with C and D in place of A and B. Notice that these exponents are not, however, the coefficients of the balanced equation. If we write these two terms together to show that the forward and reverse rates are equal, like an equilibrium, and solve for a single constant, we get something that looks very much like an equilibrium expression. For mathematical reasons, the exponents don't translate, but yeah, basically this is where the equilibrium equations come from. Pretty cool. But if it's that simple, why don't all reactions just go to an equilibrium state and stay there? Well, sometimes the reverse reaction isn't thermodynamically spontaneous for one reason or another. Sometimes the forward reaction is so vigorous that any reactants that might reform are immediately pushed back into products. Or the products might physically separate and have little chance of colliding at all, like when products separate into solids and gases. Often though, it's just that the reverse reaction has such a high activation energy that the collisions are almost always ineffective. Because remember, most reactions don't happen instantly, boom, all at once. Instead, they happen in steps. And as with any multi-step process, the reaction can only happen as fast as the slowest step takes. And sometimes that step is very slow indeed. Since it's what controls how fast everything else can go, we call it the rate limiting or rate determining step. The slowest step is the one that has the highest activation energy. If the particles have trouble getting over that part of the energy hill, then they'll have trouble making it to the finish line, no matter how fast the other steps are. So in the case of the nitric oxide reaction we've been discussing, there are actually 3 steps. First, the nitric oxide and the H2 form water and elemental nitrogen. Then the nitrogen combines with another molecule of NO to form N2 and elemental oxygen. Finally, that atom of oxygen combines with another molecule of H2 to form water. Here, step 2 is the slow one, and no matter how fast you take the first step, the water product can never be produced until the nitrogen gas is. Problem is, we can't always afford to wait around for reactions to happen on their own. Sometimes they need to be forced along, and that's the job of catalysts. A catalyst is a chemical that lowers the activation energy of a reaction, thereby speeding it up without actually being changed by it. Catalysts take many different forms. They can be just another chemical added to the reaction vessel, a piece of metal that's in contact with the reacting chemicals, or even a gas that's added to the environment. One of the most common and important classes of catalysts are the enzymes in living things. Without them, many of the chemical processes that our bodies must do every day to keep us alive would slow essentially to a stop. We literally could not survive without them. So there you go. In demolition derbies and in chemistry, it all comes down to how hard you can hit and how well you can aim your punches. Chemistry, surprisingly exciting, even without funnel cakes. Thanks for hanging out for this episode of Crash Course Chemistry. If you paid attention, you learned that chemical reactions depend on collisions between molecules and atoms, that the particles have to be oriented correctly when they collide, and that they have to collide with enough energy to meet the threshold for the reaction known as the activation energy. You also learned how to write rate laws and figure out their exponents and how to calculate the form or order of a rate law. You learned how rate laws are related to equilibrium expressions, and finally, you learned that chemical reactions actually happen in steps, that the slowest step determines the overall rate of the reaction, and that the reason for that comes right back around the activation energy. This episode was written by Edie Gonzalez and edited by Blake DiPastino. Our chemistry consultant is Dr. Heiko Langner, and was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Michael Aranda, who is also our sound designer, and our graphics team is Thought Cafe.
Okay. Right, so in 10 minutes, he covered more than I cover in like an hour and a half. He covered like 2-3 hours worth of stuff. But that was fast, right? So hopefully the first part of that sounded familiar. Like, okay, yeah, the rates and the orders and stuff like that. I would expect the last half of it to be, huh? Because that's the stuff that's coming up in the chapter. We haven't gotten there yet. But any questions about the video? Have any of you ever been to a demolition derby? Yeah? They're pretty gnarly. I'm not a big fan. I think I went to one when I was a kid. A demolition derby is when you get a bunch of guys in an arena with their cars and they smash into each other, and the last one that keeps moving is the winner. So all of the other ones don't work anymore. Yeah. Well, a little bit. Okay, so the frequency factor has 2 parts. The orientation is the fraction of collisions with a favorable orientation, and then the collision frequency, which is typically around 10 to the 9 per second. So, that A there, that was too simple, wasn't it? It's actually 2 terms, orientation and collision. We are not going to do calculations with that, but we do want to understand how orientation affects the rate of the reaction, affects the rate constant. So like he was saying in the video with the cars, in order to have an effective collision, you have to have the correct orientation. If you're running into a guy's trunk in a demolition derby, you're not damaging his car very much, and you're probably damaging your own car a lot. When these molecules bump into each other, they have to be bumping into each other, colliding in the right way. So here, if the oxygens are bumping into each other, the nitrogens? Yeah. Yeah. No, nitrogen's blue. I don't know if they did these right. Whatever. We'll stick with red and blue. If the red ones bump into each other, nothing's going to happen. If a red one and a green one bump into each other, nothing's going to happen. We're only going to have an effective collision if a green one bumps into a green one, because those can react and they're going to form the Cl2, and then we're going to be left with NO. So the blue and the red will get kicked off. So it has to be in the right orientation. For this reaction, that factor happens to be 0.16. If the orientation factor is small, it means that the molecules have to be aligned in a very specific way. If we have a reaction between individual atoms, not molecules, then that orientation factor is going to be really close to 1, because atoms are symmetric. They're spheres. So you can't say, well, you bumped into the wrong side of the hydrogen atom. What's side? They're all it's the same all the way around. So two atoms bump into each other. There's no alignment issue. There's no orientation issue. Strangely, it's also possible for the orientation factor to be greater than 1, which means that an actual collision is not necessary. What? I told you about it, that's all we're going to deal. Okay, this is the kind of question that could show up on an exam. Which reactants do you expect to have the smallest orientation factor? So what is the orientation factor? Is it big if we have to be very particular, or is it big if it doesn't matter? Big if it doesn't matter. So this is going to be between 0 and 1. So if it's 1, it's not going to affect things much at all. And if it's like 0.5 or 0.16, it's going to slow things down, right? So if we need a particular arrangement, we're going to have a small orientation factor. If it doesn't matter, we're going to have a big orientation factor. That's something you have to get straight in your head. Okay, so smallest orientation factor, we're looking for the most complicated. Which of these is the most complicated? It's C. This is 2 atoms. That orientation factor is going to be close to 1. Here we have an H2 and an I2. There's going to be, some orientation issues, but one end of each molecule is the same as the other end of that molecule. But here we have HCl, and we either need the hydrogens to run into each other or the chlorines to run into each other, depending on the mechanism. And so that's not going to happen as much. So that's the smallest orientation factor.